Hello, geometry students, and welcome to our first lesson together. You'll notice that I broke it up into two parts just because it's such a concept and vocabulary heavy lesson. So the first part is about measuring segments, and our learning target states that we can use the properties of segments to determine their measures. Some of the main takeaways from this lesson are going to be our undefined terms. That's our points, lines, and planes. We're going to be talking about measuring segments, using the segment addition postulate, and midpoints and their significance. You should be following along with our fill-in-the-blank notes. As long as you are working through the notes with me, you should know exactly what parts we are covering here. So let's get started. So the first undefined term we're going to talk about are points. And points are just locations. Let me write that down here. Point is a location, just somewhere in space. Usually when we think of points, we think of coordinates on a grid. That's a good example of a point. But a point has no size or shape. It is just a location, nothing more. We always use a capital letter to name a point. So for example, using the point A over on the left column, we can call that either A, capitalized, or point A. Like that. Now let's introduce lines. A line is made up of points. You can see on the diagram to the left, there are points X and Y on this line. Any 2 points form a line. There are at least 2, but honestly lines go on infinitely, so there are infinitely many points on a line. A line has no thickness or width. It is just a string of points that goes on infinitely in 2 opposite directions. So when we name a line by any 2 points on the line or a lowercase script letter. So for the example of this line here, notice the script letter is N. So we would call this line N. And script is just a way to say cursive. So line N. We can also call this line XY. Remember, with capital letters for the points. And we can also call this line XY, but with some notation over the top of these letters. So when we make this notation, we have arrows pointing in opposite directions. This is how we determine that this is a line. We do need to mention collinear points and non-collinear points. Collinear points lie on the same line. So in our example, X and Y are collinear points. Non-collinear points are at least 3 points that do not lie on the same line. So in example here, let me draw another point. So this is point Z. We can safely say that since Z is not collinear with X and Y, X, Y, and Z are non-collinear points. They are non-collinear. And another undefined term we will be using this year are planes. A plane is a flat surface made up of points. Any 3 points make up a plane. And when we think of planes, it kind of looks like a sheet of paper. It's a flat surface, but honestly it goes on infinitely in every single direction. It extends indefinitely It's a never-ending piece of paper, I guess we can call it. We name planes by any 3 non-collinear points on the plane, or an uppercase script letter. So we need to find 3 points that are not on the same line, or the uppercase script letter. So in our example, when we name this plane, this is either plane P with a script or cursive P. We can call this plane KJL, as long as we are using 3 non-collinear points to label this plane. Coplanar points are points that lie on the same plane. Non-coplanar points do not lie on the same plane, so at least 4 points. Here's an example of non-coplanar points. Let's say I have point M. Point M. Notice how point M, spatially it's hard to see, but point M is below this plane. So K, J, L, and M are non-collinear points. Or sorry, non-coplanar points. Let me adjust here. Now, lines and planes intersect, and they intersect at specific places. 2 lines will always intersect or may intersect at a point. So in the case in our diagram here, lines R and S intersect at point P. 2 planes intersect at a line, kind of like 2 pieces of paper crossing each other. They intersect at one specific line. And of course, there are infinitely many points on a line. So let's practice using these undefined terms. Number 1 says we are going to use the diagram to the right to name the following. So 1A says we need to name 4 collinear points, or 4 points on the same line. Well, I see right away this line here. And I see H, N, K, I. These are all collinear. H, N, K, I. A line that contains point M. Well, here's point M. And the line that I see that contains point M, we can call that a few things. We can either call it line P with the script letter, or we can call it line MN, MO. We can call it any combination of those things. But just for now, I'll call it line P with the script letter. Now we need to find a line that contains points H and K. I think we already identified that line. The line that identifies or that contains points H and K, we can call it line HK, we can call it line NK, or we could just call it by the script letter line R. So I'll do that. This is line R. Another name for line Q. Another name for line Q, like I said, you can use any combination of 2 points on this line. So let's give 2 examples here. Let's call this either line JL, and this time I'm going to use the notation with the line above the letters. Or I can call this line JK without the line over the top of the letters. Either notation is fine. And the intersection of lines P and R. The intersection of lines P and R, if I look at this diagram, P and R are intersecting right here at point N. And so we can either write out point N or we can just say N. I'm going to save number 2 for you, and if you would like to practice some additional problems, you can go on to numbers 3 and 4, and there are more problems that are having you identify undefined terms and specific vocabulary. So stop here and practice before moving on. Let's get into measuring segments. So a segment is just a portion of a line. It has specific endpoints. So we can see on this number line here, we have segment AB. And we are going to measure segment AB. The distance between 2 points A and B should be written as the length of AB, like so, the length of AB. And the notation for a line segment looks like this. It's just a bar over the endpoints of the segment. So we can call it the length of segment AB, or without the notation, this is just AB. AB just means length of AB. So over on the right column here, let's just measure this segment. Point A is at -1, point B is at +3. The distance between those points, if you subtracted or took the difference of those points, would be 4. 3 minus -1 is +4, or the absolute value of -1 minus 3 would be 4. Let's talk about congruent segments. Congruence, for the record, means same measure. Congruence means same measure. If in this diagram we have segments AB and CD, it looks like they are the same measure. It looks like they are 4 units long each. So if the length of AB is equal to the length of CD, then the segments are congruent. This is written as follows. We can say AB, segment AB, with the notation on top, and CD, again, line segment on top, are congruent. The symbol for congruence looks like this. You have a tilted line, or a squiggle, if you will, and then an equal sign below it. So squiggle, equal sign. I know that's not very mathematical terminology, but it's a great way for you to remember the symbol for congruence. All right. Moving on to the segment addition postulate. You'll notice off to the right here, we have line segment AC, which is a combination of AB and BC. If A, B, and C are collinear points, meaning they're on the same line, and B is between A and C, then the following is true. We know that the length of AB, that's AB without the line segment on top, plus the length of BC is equal to the entire length of AC. In other words, part plus part is equal to whole. I know that seems pretty straightforward, but this segment addition postulate, meaning this property, is something we're going to be using very often, and it's important that we know this specific line of reasoning. So let's look at some examples. Let's apply the segment addition postulate and how to measure these segments. So looking at the diagram here, we have segment PR with portions PQ and QR. Number 1 says if PQ is equal to 9 and QR equals 28, find PR. Well, if PQ is 9 and QR is 28, that means we just need to add up these segments in order to find the length of the entire segment. So 9 plus 28. and that's equal to 37. So the length of PR in this scenario is 37. Let's do another color here. If QR equals 17 and PR equals 21, we need to find PQ. So if QR is 17, if this part is 17, and if PR, the entire segment, is 21, we need to find PQ. So using that segment addition postulate, we take PR minus QR to find PQ. So 21 minus 17, and you get 4. Let's try a couple more. We're going to add some algebra in here. So with the segment addition postulate, it's really important that we are modeling equations with the specific line segments before we add in the terms. So here's what I mean. For number 3, if EG equals 71, if the entire segment is 71 units, we're asked to find the value of X. So here's what I'm seeing. I know that EF plus FG, part plus part, equals whole, or EG. So now I know exactly how to write my equation. EF is represented by the expression 8x minus 17. So 8x minus 17 plus FG, which is 5x minus 3, is equal to whole, EG, which is 71. And from here, we can solve algebraically. Let's combine our like terms. I know I need to combine 8x and positive 5x to get 13x. I need to combine negative 17 and negative 3. Adding them together gets me negative 20. So 13x minus 20 equals 71. Now I'm going to eliminate the negative 20 by adding it to both sides. This cancels out. Now I have 13x is equal to 91. And now I need to divide both sides by 13. Great algebra review for everybody. 13 divided by 13 reduces to 1, and x is equal to 7. All right. For number 4, I am just going to model how to set up the equation. I will let you solve that equation to find TU. So it says if TV is equal to 14x minus 8, meaning the whole segment is 14x minus 8. And we know that TU is the expression 9x plus 2. UV is 5. We are asked to find TU. We need to set up an equation first to solve for x. Then when we find x, we can substitute that value to find TU. So I'm seeing part 9x plus 2 TU plus UV, which is 5, is equal to TV, the entire segment, which is 14x minus 8. And from here, I am going to leave that up to you to solve. Once you find x, you need to substitute the value of x in to the expression for TU, which is 9x plus 2. You can check my answers later. If you would like additional practice with this concept using the segment addition postulate, numbers 5 through 7 are excellent practice. Again, I recommend that you are modeling the equations with the line segment names first, and then filling them in with the expressions in the diagram. All right, let's talk about midpoints. So, the midpoint of a segment, is a point that divides the segment into two congruent segments. And when I say two congruent segments, I mean segments that are the same measure. So if we look in this diagram here, the line segment AC is divided evenly by line L. The midpoint of segment AC is point B. And notice these tick marks. There are little dashes that go through the congruent parts of segment AC. This is the universal symbol for congruent segments, tick marks. A line, ray, or segment that intersects a segment at its midpoint is said to bisect the segment, meaning cut into two parts. Bi means two, sect usually means cut. The segment and is called the segment bisector, meaning this is a specific specific line, ray, or segment that divides the segment in half. Segment bisector. In the diagram to the left, just to really make it clear, B is the midpoint of segment AC, and I'm going to use the line segment notation here. And line L, using the script letter, usually script L is kind of a loop-de-loo here, and line L is a segment bisector of AC, segment AC. Okay. So let's take a look at some examples of midpoints. For number 8, it says if Q is the midpoint of segment PR, we need to find the value of X. So we're already told point Q is cutting segment PR in half. I know that PQ is congruent to QR. Congruent means same measure. In this case, we can say PQ is equal to QR. So we modeled with our segment names. Let's put it in algebraically. So PQ is 7x minus 16, and that is equal to QR, which is 4x plus 2. So now we need to move variables to one side of the equation and constants to the other. Let's move positive 4x over by subtracting it from both sides. This is eliminated. And we have 3x minus 16 is equal to 2. Moving the constants to the right side of the equation, let's move the negative 16 by adding 16 to both sides. This cancels out. We're left with 3x is equal to 18. We need to divide both sides by 3. And x is equal to 6. There we go. An additional practice problem for you to apply algebra to finding midpoints is problem number 9 directly after this problem. Go ahead and take a second if you would like to practice that now. All right, so that was part 1 of our lesson. Thank you so much for watching. So if you have not done so already, try out the additional practice problems I referred to in blue at the end of each slide. You can check your answers with my filled in notes. I will be putting those in our class notebook in the content library, and then navigate to topic 1 notes. You will find it directly in that file. If you need a little bit of extra support, just ask me in the math help desk if needed. But with that being said, I will see you for part 2, where we are measuring angles.